just talks about kind of how it works, the pieces involved. It's quite a process. And then the next section, 8.3, actually talks about testing hypotheses about a proportion. And then 8.4 talks about testing hypotheses about a mean. So it's going to be analogous to the confidence intervals.
So we're just doing one section today?
We're going to do as much as we have time for.
Okay.
So first of all, 8.2, 8.1 is your review preview where they say, oh, okay, back in chapters 2 and 3 we did descriptive statistics. And yeah, 8.1 is just the intro. So 8.2, what about 8.2?
It's just a pretty too.
Aw, thanks. Is the basics. The logic, the process. 8.3, testing claims about P. And for that, we're going to use one prop Z test, right? We used one prop Z int for confidence intervals involving P. One prop Z test for testing a claim. And then 8.4, testing claims about mu, a population mean. We're either going to use t-test if you're given S, and z-test if you're given sigma. So very analogous to the intervals where we use t-interval and t and z-interval in those same cases. But confidence intervals are just a calculation, and hypothesis testing, like I said, is a process. So here's how it works. You start with a statement about the population parameter. It's going to be about P or mu.
So this is talking about A2.
This is talking about the process in general that is going to be in 8.3, 8.4, and the section in 9.3. But yeah, 8.2, the basics. I would say definitely read this. Hopefully you're reading your book from time to time, but that's a good section to read. So you start with a statement. Let me kind of run through an example as I tell you the pieces, and I think that'll make more sense, and we'll eventually get to the PowerPoints. So, for example, heck, let's use my my political statement here. Suppose 100 registered voters. Let's make it 1,000. Are polled, and let's say, suppose 49% of them say they are voting for Hillary Clinton. All right, so I haven't gotten to the statement yet. Test the claim that more than that's not gonna work. Less than well, let's just test the claim that half of voters will vote for Hillary. All right, so that's our statement. That's our hypothesis that we're going to test. So the first thing you want to do is write it in symbols. This one is about a proportion. So we use the symbol P for population proportion. And what is this claim in relation to P? It's saying that half of the voters, half is 50%. So this claim is actually that this proportion is equal to 50%. Or 0.5, on the right, 0.5. Alright, so do that first. Then, if, as it is in this case, that statement involves equality, then it becomes the, what we call the null hypothesis. Which is denoted by H sub 0, which is going to be the underlying assumption for the test. So we're going to assume that's true. Now, if that statement, that claim, involves not equal, greater than, or less than, then it becomes the alternate hypothesis. The alternate hypothesis is denoted by H1. Okay. The null hypothesis always has to involve equality. So like if I had left it the way I started as more than half, that would have had to be the alternate hypothesis. Your underlying assumption for the test has to involve equality to some value, because that then gives us a baseline for the sampling distribution that's used for calculations. So we have this underlying assumption about what this parameter is actually equal to. And then we look at some sample data. So you're also going to be given some sample data, like here. So you're given sample data. In this case, we have n equal to 1,000. We have p hat equal to 0.49. And so what would x be in this case? How many is 49% of 1,000? That's 0.49 times 1,000.
4.8. Or no.
It should just be 490. 490? Okay, we're gonna need that for one prop z test, just like we needed it for one prop z int. So given sample data, you're gonna go to the test in your calculator, and the calculator is going to calculate a couple things for you. The calculator will calculate something called the test statistic, which is either going to be a t-score or a z-score, based on whether we're having to use this new t distribution or whether we can use the normal distribution. In proportions, it's going to be a z-score. For means, it's either going to be a t-score or a z-score, depending on whether you're given s or sigma. This test statistic tells you where on the distribution, on the sampling distribution, your particular sample statistics lie. So you've got this sampling distribution of all samples of size 1,000. question is, where's our sample on this distribution? If our distribution is centered at actually the mean, which would be n times p, in this case it's like a binomial, it's centered at 500. 500 out of 1,000 is what we're assuming would be the number of people who would vote for Clinton if this is true. Right? Because we're assuming this is true. We're assuming the null hypothesis, this is h sub 0 right here, is true. H1 in this case is just going to be that it's not equal. They're opposites in some sense. Alright, so what's going to happen is your calculator is going to calculate this t-score or z-score. Here it's going to be a z-score for where is 490 on this distribution, right? So it's down here somewhere. We don't really know. There's a lot that plays into it. The sample size plays into it, and well, the standard deviation, which is actually the square root of NPQ, like a binomial. But it's calculated with this formula that's going to tell us where 490 is. It's the t-score, z-score. It's going to actually be a z-score for that position. So it'll tell us basically if that's extreme or not. How far to the left of the distribution is it? Then it's going to calculate the p-value. The p-value is a very important measure. The p-value is the probability beyond that test statistic, either to the left or to the right if it's over here, or in this case, where we're looking at equals versus not equals, it's actually going to calculate it in both directions. What the p-value gives you is the probability of getting this sample if the null hypothesis is true. So under the assumption that the null hypothesis is true. If the null hypothesis is true, what's the probability we actually would get this sample? Alright, there's sample variation. So the question is, is this something that should happen under the assumption of the null hypothesis, or is it unlikely? If the p-value is what I call too small to believe, then our conclusion is going to be to reject the null hypothesis, because that means that that shouldn't have happened, basically. If the p-value is like really, really small, that would say this is really far off the distribution, and that is so unlikely that we must have been wrong in our original assumption. It's that rare event rule for statistics. If under some assumption, like the null hypothesis, the occurrence of some event, like this sample, is really, really small, then we reject the original assumption. We think, well, we must have been wrong in the original assumption. So we reject HO. And HO and H1, the null and the alternate hypotheses are the opposites of each other. So in that case, we would support, or say our evidence, our sample data supports H1. If the p-value is not too small, and I'll tell you what we're going to call too small in a minute. If the p-value is not too small, then that could happen. And we can't reject the null hypothesis. It might be true. Can't reject HO, and so then we'd have to say also that we can't support the alternate hypothesis. So you can kind of see there's four kind of possible outcomes to the test, depending on the p-value p-value, and depending on whether we care more about HO or H1. Sometimes the claim's gonna be HO, sometimes the claim's gonna be H1. Okay? So if the claim is our null hypothesis, then we either reject it or we say we can't reject it. And actually that's worded in terms of not enough evidence. And then I'll show you the best way to word the final conclusion. Okay.
Are we doing all this in our calculator?
These calculations right here, we are.
And then that'll determine if we accept or reject the null hypothesis?
If you reject, you don't actually accept it, but you either reject it or you can't reject it. So it's kind of just slightly different. So you're gonna have to be careful about the wording of your conclusions. Either you say there's not enough evidence to reject HO and support H1, or there is enough evidence to reject HO or support H1. And these hypotheses, again, one of them's gonna be your claim and one of them's not. So you're gonna start by setting up which one's which based on the claim. You're gonna identify the sample statistics. You're gonna plug them into your calculator, calculate your test statistic and your p-value. And then you have to conclude whether the p-value is too small or not. And here's another very important thing. This idea of too small is gonna be measured by alpha. Remember alpha, the significance level? So you're also going to be given, somewhere I need to put up here, also given alpha. Alpha is usually 0.05. 5% level of significance, if you remember, corresponds to a 95% confidence level. It's the complement of how confident you are. So it's kind of like a probability of being wrong. So too small to believe is just less than alpha. And not too small is greater than alpha. Again, alpha is usually 5%, but it could be anything. It's usually 0.05. That's the most common level of significance. That's what we've been using for unlikely, right? Unlikely or unusual, less than 5%. So that's what's typically used. But sometimes we want to be really sure, so then we use a 1% level. That's like a highly statistically significant level, corresponds to a 99% confidence interval. So anyway, you're going to be given alpha so you can do this comparison and decide whether the p-value is too small or not. Alpha is like our measuring stick for what's too small. Okay. Alright, so let me run through this actual test of this actual statement here. So this is one prot z test. Going. Back on. One prop z test is on that first list when you go to stat and test. Let's warm up again. I have a feeling this one is actually going to be a pretty big p-value because 49% is pretty close to 50%. All right, so option 5 is one prop z test. All right, so it asks for the same thing that the interval did, except for it also asks for this p sub 0. P sub 0 is the hypothesized proportion in the null hypothesis. Okay, that's what we're assuming the proportion is actually equal to for the purposes of calculation. That's like where the distribution is centered.
How do we know that we're supposed to use one prop z test?
Anytime you're testing a claim about a proportion.
Okay.
that's the case we're in here, because I'm a half testing the claim that half voters are voting for Hillary, so it's a proportion. Alright, so 0.5 is what we're actually assuming the proportion is. It's also our claim. And we happen to have a sample, supposedly, of 490 people that say they are going to out of 1,000. Oops, not 10,000. Alright, then it asks which one is your alternate hypothesis, okay? Because that tells it how to calculate the p-value. If our alternate hypothesis was actually that it's less than 50%, then we would choose this one. P sub 0 again is the 50%. Portion is what we're comparing to P sub 0. If it were less than 50%, then it would just calculate the area beyond that to the left. If our if our alternate hypothesis was that it's greater than, then it actually calculates it to the right. And for just equals versus not equals, because this one wasn't anything about more than or less than, I just said half, we select this first one, highlight it, hit enter, so that it will calculate it in both directions. So basically, if it's too extreme in on either side, we would reject HL. So then calculate. I'll show you draw also. So H1. So remember I said the alternate hypothesis is always going to be either not equal, greater than, or less than. So the null hypothesis is always going to be even. All right, so everybody got those selected on there?
So is Z value always to the right?
No. No, in fact, this one's to the left.
Oh, to the left. Oh, okay.
Yeah, it depends on where the sample, yeah, where the number is for the given situation.
Okay.
Alright, so when you hit calculate, hopefully you get the same thing.
Yep.
This tells us that the z-score, or test statistic, is, let me use a different color, negative 0.632. So that's less than a standard deviation to the left of the mean, so that's actually maybe here. So our p-value is going to be big because it's actually then going to double that. Yep, 0.527 is our p-value. So again, that's the probability of getting this sample data if the null hypothesis is true. So basically, that's going to happen more than half the time, right? 52%, that's a probability. 52.7% chance of getting this sample data if the null hypothesis is true. Since that could happen, that's not too small to believe. I didn't even tell you what to use for alpha, but definitely if we used alpha equal 0.05, which is the typical one, it's not smaller than that. So we're in this case where it could happen, and so the null hypothesis might be true, we can't reject it. So that means we can't support H1 either. This one, we're looking at the claim being the null hypothesis, right? Because I worded it in terms of, half, equals half. So the final conclusion then would be that at whatever level of significance we're using, at alpha equal 0.05, let's say, at that level of significance, there is not enough evidence. Right? It was not extreme, so we say that there's not enough evidence. The p-value was not less than alpha.
Would we ever change alpha? Or
No.
just always use that?
Use what they give you. Use what they give you. For each problem, they'll say use a certain level of significance. And then in your final conclusion, you want to restate what they told you to use, because that's like, the deciding factor for the conclusion. So restate whatever they tell you to use for alpha, you're gonna say either there is or is not enough evidence, okay? We have not enough evidence, why? Cause our p-value was not smaller than alpha, it was not too small to believe. When it's too small to believe, that's when you do have evidence, that's when you have statistical significance. This idea of when it's really small, that's statistically
So
significant.
whatever p is smaller than.
So that's when you have evidence. So there is evidence here. A small p-value is typically what you want to say, ooh, that shouldn't have happened, that's more decisive. So here there is evidence. Whereas when you get a p-value that's bigger than alpha, it's like, well, we don't really know, right? That could happen, it's not too unusual to believe. So it's more inconclusive. Not enough evidence, this is more the inconclusive situation when you have a large p-value. Right, and then you look at which one's your claim. Our claim was HO, so we say to reject it, to reject the claim. And then I also want you to restate the claim in words. So that half of voters will vote for Hillary. That might be true, just we don't have evidence against it. Okay, let me show you another one. Actually, let's run through the PowerPoint. Because the PowerPoint has another example. Alright, so again, 8.1 is just your review preview. Let's see what it says. In chapters 2 and 3, we use descriptive statistics when we summarize data using tools such as graphs and statistics such as the mean and standard deviation, right? We just did calculations. Methods of inferential statistics use sample data to make an inference or conclusion about a population. And the two main activities that we're looking at here are estimating a population parameter, such as confidence intervals, that was chapter 7. And the other type of inferential statistics involves this testing claims, which is what we're doing now. So yeah, chapter 7, we did the confidence intervals. And the main objective is to develop the ability to conduct hypothesis tests for claims made about a population proportion P or a population mean mu. Here's some examples. In genetics, the Genetics and IVF Institute claims that its XSort method allows couples to increase the probability of having a baby girl. So that's actually where they're claiming that the proportion of people that have a girl when they use this method is more than 50%. So that's a claim about a proportion of probability. This one is similar actually. It's a business situation. A newspaper cites a pricegrabber.com survey of 1,631 subjects and claims that a majority have heard of Kindle as an ebook reader. Majority, what does majority mean? More than 50%. So again, that's claiming that P, this proportion of people who know about Kindle, is more than 0.5. Alright, and then here's one about a mean. So these two are about proportions, very similar to what we were doing here. This one is often claimed that the mean body temperature is 98.6 degrees. We can test this claim using a sample of 106 body temperatures with a mean of 98.2 degrees. So this is the claim that mu is equal to 98.6. So that would be another null hypothesis. These two would be alternate hypotheses because they are both that P is greater than 0.5. So those would be alternate hypothesis types of claims. And that's important to notice because the wording of the conclusion when you have an alternate hypothesis is that you get to either support it or word support, which is typically a more positive word to use. You can only use support in your conclusion if your claim is an alternate hypothesis. If your claim is the null hypothesis like ours, and this one, then the best you can say is either reject or fail to reject. So you wanna remember that, you know, it matters what your claim is, if it's HO or H1, for how you word your conclusion.
So for the business one,
Mhm.
to know that we're using the alternate hypothesis, it says that a majority has.
Mm-hmm. Usually they're gonna be a little clearer. Majority is kinda, you gotta go, oh, that means P is greater than 0.5. But yeah, that's exactly why.
And then which one would we use, the null hypothesis?
This one, cause it says is, as opposed to more than or less than.
It has to be equal to.
Yeah, and this one uses the word increase the probability to greater than. Alright, so that's that. And let's look at the basics. There's a few things in here I haven't talked about yet, so I might skip her stuff. This one. Fact. No, let's see how far we get. Alright, so section A2 presents the pieces, the individual components of the hypothesis test. Identifying the null hypothesis and alternative hypothesis, how to write them in symbols. You wanna make sure that you use either P for a proportion or mu for a mean. And then it's gonna be equals, not equal, less than or greater than. And some number. Alright, so how to calculate the value of a test statistic, that's where we're gonna use a calculator. They're gonna talk a lot about the sampling distribution that's relevant, and in practice you do have to choose whether you want the normal distribution or the t-distribution. For us, it's gonna be pretty easy, just what we use in our calculator. And it's, for the proportions, it's always gonna be one prop z test. For the means, like I said, either t-test or z-test based on whether you give an S or sigma. So it's not that big a deal. Identify the p-value and the critical value. We're not gonna do the critical value approach, we're just gonna use the p-value approach since that's what the calculator gives us. And then stating the conclusion correctly is what I was talking about over there. Restating alpha, whether there is or is not enough evidence, whether you reject or support the claim, and what the claim is. Alright, let's get some definitions. And hypothesis is a fancy word for a claim or statement. About something about the population. Hypothesis test is this procedure for testing the claim. Here's the rare event rule that's being used. That's the logic here. Is if, under a given assumption, like your null hypothesis, the probability of a particular observed event, like a certain sample data, is exceptionally small, smaller than alpha, then we conclude that the assumption is probably not correct and we reject it. The null hypothesis, again, H sub 0 is always that the parameter, either P or mu, we're not gonna do standard deviation claims, is equal to some value. It's gotta give us that baseline value for the center of the distribution and the calculation of the p-value. So, in a sense, we're really testing the null hypothesis, whether that's our claim or not, to see whether we should reject it or whether we can't reject it because it's not too unlikely. That's actually another way you can view the p-value is the probability that the null hypothesis is true, right? It's more technically the probability of getting that sample under the assumption that it's true, but you can kind of say, well, you know, if it's small, that means the null hypothesis is probably not true. So this, you know, this could happen. Can't reject it. The alternate hypothesis, we're calling it H1. Some books and places use HA for alternate. But it's the statement that the parameter has a value that somehow differs from the null hypothesis, either less than or greater than or not WHO, we support each one, the different one. Little tip if you're doing your own hypothesis test and out in the field doing research, that you should probably state your hypothesis or claim as an alternative hypothesis so that you can use the word support. I used to have people do projects, I'm not gonna go over that one. I used to have people do projects in this class, but with the 7 weeks, there's not really enough time. You know, I would say, okay, start collecting data, we'd spend a few weeks collecting data, and then we do a hypothesis test based on that data, but 7 weeks, not so much, it's too bad. Alright, so in this example with the babies, with the XORT method, that says that they can increase your chance of having a girl, not so sure about that, that they say suppose that we've got 100 babies, and 58 of them had girls, 58 of them were girls. So, well, that's more than 50%. But then the question is, well, is that enough more than 50% to say that it's actually true for the population of everyone who uses this method, and therefore say that the method really works? It's like, it kind of looks like it worked for this sample, but you know, that could just be due to variation. You know, sometimes you have more girls than boys, it happens. So here's where we kind of look at, well, what's the probability if there's really a 50% chance? What's the probability of having 58 girls and 100 babies? If that could happen, then we say, well, it's, you know, it's probably true that it's still just 50%. Whereas if it's like really rare that that would happen, then we go, ooh, that must be false. We must reject that and go with saying that the XORT method really works. Anyway, the setup, just to, you know, streamline it, is that they are wanting to claim that the proportion of girls is more than 50%. So that's the claim, right? And because it's greater than, that's the alternate hypothesis, because the null hypothesis always has to be equal. So that's the setup for this particular claim. P is greater than 50% is what they're claiming. That's the alternate hypothesis. The null hypothesis is equals. All right, the significance level alpha, again, in practice, you would choose based on how serious it is to be wrong in some sense. You're going to be given alpha though, and it's usually 0.05 and 0.01. That's the significance level. And yeah, they say it's the probability that the test statistic will fall in the critical region. Skip that. These are formulas that are built into your calculator's tests. Aren't you happy? You don't have to use any of these formulas. We used to have to do that. Those are the formulas for the test statistic, for the z-score, the t-score, that measures where the sample data is on that distribution. So one way to make the conclusion is to compare the z-score to something called a critical value. But it's the same as comparing the p-value to alpha. So we're just going to compare the p-value to alpha.
And did you do that, Dr. West?
What's that?
All of those formulas?
Oh yeah, yeah. No, in fact, here at Tech, we used it pretty recently.
They
When
still do,
yeah, some people still do.
because I took this
Yeah.
last semester and we had to do all of
Mm.
them.
Man, I don't do it anymore. Yeah, you know, I obviously show you, and I put the formulas in your handout too, so you can see that this is what's going on behind the scenes, but I don't think that, you know, you wanna spend all this money on a calculator and then not use it to its full ability.
Personally, sorry, they put you through that.
It's really, those formulas aren't bad. Remember the correlation coefficient? That was a bad formula. So, alright. So here again is that example with the XORT method of gender selection. So there's 58 girls and 42 boys. There's actually a binomial here that we're approximating with a normal distribution, just FYI. Here's the setup, and then here's the sample proportion. proportion, p hat. Here's actually the formula calculation of the z-score for that situation. Let me show you. Calculator. We go to stat, test, one prop z-test, 5. P sub 0 is still 0.5 for this problem. X is now 58, the number of girls, out of 100. And now the alternate hypothesis is that the proportion is greater than P sub 0, greater than 0.5. Alright, so if we calculate that, there's that z-score, 1.6. That they were just got from the formula. And then this is the p-value that's actually the area to the right of that. Right, let me show you the draw option. When you go to any of these tests, you have a calculate option and a draw option. If you go down to draw, arrow to the right, and hit draw, it actually draws the sampling distribution
That's cool.
and shows the main calculations. The z-score is that position, and the p-value is the area that it shades.
That's cool.
Yeah.
Hey, that's actually a bell shape.
Yep.
Yeah. Very cool.
Alright, so that's what they're calculating here. And they kind of reason it out. They go, at first glance, 58 girls and 100 boys does not seem to support the claim. Let's see. Tails. Here are the types of situations of how the p-value is calculated. Again, kind of behind the scenes, you've got this bell-shaped curve. If it's equals versus not equals, like the one we did with the voting, that's where it calculates it in both directions. And basically, if you're too far in either direction, you would reject HO and support H1. A left-tailed test is when you have equals versus less than. And then your test statistic is typically over here. Your p-value is the area to the left. And again, if your p-value is too small, that would mean you're too far to the left, and you would reject HO. Whereas if it's equals versus greater than, your test statistic and p-value are going to be calculated to the right, and you would reject HO if it's too far to the right. Alright, so yeah, p-value is the area beyond the test statistic in one direction or both. And we reject the null hypothesis if the p-value is too small to believe. They say very small, smaller than F. Alright, so back to this example, we got the setup, there's the test statistic, and there's the p-value. Test statistic again kind of gives the position, 1.6 standard deviations to the right of the mean. P-value is that probability of being at least that extreme. We don't need that. Critical region, we're not going to use. Critical value is actually the cutoff for alpha. So there's two ways of looking at it, and actually it's probably a good idea to kind of go over this in case you see this critical value. The z-score that cuts off alpha, you find that with inverse norm. So if you took inverse norm of 0.05, you would actually get the one down here. You would get a negative 1.645. So the cutoff for 0.05 to the right is 1.645.
Just take the positive, in other words, what you're saying.
For a right-tailed test, yeah. So this is this region, sometimes called a critical region or a rejection region. If your sample statistic is in that region, beyond that critical value, then that would correspond to too unlikely to believe. So you can either compare your test statistic to the critical value to see if it's too far off the chart, or you can compare the area of the critical region, which is alpha, to the area beyond the test statistic, which is the p-value. So it's like, do you want to compare numbers on the number line, or do you want to compare areas? We're going to do the comparing the areas, the probabilities. alpha is what we're saying is too far off, that's the, too unlikely. If the p-value is less than that, then that's definitely too unlikely to believe, and we reject HO. Whereas in this case, it was not too unlikely, and so we failed to reject. There is a caution about keeping your p's straight. There's p-value, there's proportion, there's p hat, right? So you do have to kind of be careful. And then the methods all lead to the same conclusion. Here's the method we're using. The p-value is less than or possibly equal to alpha, although it's never going to be equal. Reject HO, and greater than, fail to reject HO. Critical value method is just where you're comparing number line values. So here, we're going to use this method. We're going to say, well, that p-value is greater than 0.05. Close, though, huh? 0.0548 is just slightly bigger than 0.0500. So, fail to reject. Yeah, close, but no cigar. So, again, the z-scores were real close, but the 1.60 was not beyond 1.645. All right, then the conclusion. It's kind of like the final answer. Is where you want to restate alpha, and then whether there was or was not enough evidence, sufficient evidence is the word they use, and then whether you use the word support or reject. In this case, the claim was that the XOR method increases the probability, so that was an alternative hypothesis or alternate hypothesis, so they use the word support. Those four pieces. Restate alpha, whether there is or is not enough evidence, whether you support or reject the claim, and then what the claim is. And let me end this show for now and go to 3. We'll come back to that. Sometimes it gets a little too involved. We want to cut to the chase, right? Alright, so we are using a normal distribution for proportions. These are the symbols that hopefully you're getting used to. There are these certain criteria that have to be met, but you won't have to check them. They're going to be met. Turns out you need NP and NQ to be at least 5 for this to work. And then again, here's the formula that's built into your test. Use your P's. Here's the example, and this one's in your handout. If you want to follow along, this is page 7. I handwrote page numbers, because otherwise I got those funky double numbers in the middle. Page 7. Based on information from the National Cybersecurity Alliance, 93% of computer owners believe they have antivirus programs installed on their computers. In a random sample of 400 scanned computers, it is found that 380 of them, or 95%, actually have antivirus software. Use the sample data to test the claim that 93% of computers have antivirus software. Alright, so you want to notice that it's about a percent proportion, P. And the claim that they say to test is that 93% have software. So if we write that in symbols, it's P what? Equals, greater, less than?
Equals.
Equals. Okay, because they didn't say more than 93% or less than 93%, or it's not 93%, they just said 93%. So that's in symbols, and because it's equals, that's gotta be our null hypothesis. So the alternate hypothesis in this case is gonna be not equal. Our sample data, sample statistics, is a sample size N of 400 scanned computers. And statements found that 380 of them, what's that? X. Or 95%, what's that?
P.
P hat.
P hat. Excuse
Yep.
me. P hat.
So they actually gave us both in this case. If you divided 380 by 400, you would get 0.95. Alright, so they gave us both. They haven't told us what to use for alpha yet, they still need to do that. Alright, and they do this check to make sure that it's, gonna work, you won't have to do that. Here's the setup. Alright, so they are gonna use alpha equal 0.05, so I'll write that down. Okay, so you wanna write down the claim, set up, whether it's HO or H1. Write down your sample statistics so you know what to put into your calculator, and write down alpha. Then go to one prop Z test. I will walk you through that, that's the next screenshot you have in your handout. Here. Stat, test, number 5. So P sub 0 in this case is what? That's alpha. 0.93. Right, P sub 0 is the hypothesized proportion in the null hypothesis, but it's also the number in your claim. 0.93. X is, see, that's where if they only gave us the 95%, we'd have to go, what's 95% of 400? Oh, what do you know, it's 380. 400 is the total. And which one are we looking at here? Equals versus not equals. Calculates. 1.5677 is our z-score. And our p-value, which your calculator just calls p, is 0.1169.
P hat is 0.95 and N is 400.
Right. So it spits those back out at you.
Mhm.
But these are the key things, right? Your test statistic and your p-value. The p-value is what we are gonna use for our decision. We're gonna look and see if it's smaller than alpha or not. Well, is it? No, that's about 11–12% chance. That's a 5% chance, so it's not smaller. So that could happen. So we failed to reject HO. Or you could say can't reject. Fail to is what they say. Fail to reject HO. Alright, that's when there's not enough evidence. Either to reject HO or support H1. And so then you look and see, well, which one was the claim? The claim was HO, so we're gonna word our conclusion in terms of the fact that we can't reject HO. So we're gonna say at alpha equal 0.05, there is not enough evidence to reject the claim. So some of what we have over there, to reject the claim that 93% have software, have antivirus software. 93% of computers have antivirus software. Alright, let's see how they do it. Formula. They got 1.57 when they rounded the z-score using the formula, so that's what your calculator was doing for you. And then they've got the picture here. This one, the area beyond the test statistic is actually 0.0582 approximately. What our calculator did for us was then double that, because it's an equals versus not equals. It's actually what we call a two-tailed test. So So that's actually what they do here. Of course, theirs is a little off because they're using a table. So, of course, that, they got 0.1164. Alright, and it's greater than alpha, so you fail to reject the null hypothesis, which is the claim. Here's the screenshot that walks you through what we just did on our calculator. And
So
output.
the actual videos and the homework don't apply to us anymore because they're like not telling how to use the calculator. They're trying to use the formula. So I don't guess they really apply to us no more.
What videos?
The like on sometimes it'll like on the homework questions it'll have a video link and they use the table and stuff, so it don't apply.
Yep.
So
Alright, yeah, you can just use these tests. So, you know, this is just describing what your output is when you choose calculate. And if you choose draw, now you do have to be careful with the draw option. I have a note down here that says hit your y equals and make sure everything's cleared out. Because if your calculator is trying to graph something at the same time that it's trying to draw something, you're gonna get an error. So if you just hit y equals, make sure that those are all clear and that the plots are all turned off, meaning unhighlighted. Then you'll be able to use that draw option and see the curve. So you can see that two-tailed situation there. Alright, more cautions. Make sure you set up the hypotheses correctly. The test statistic and the p-value are gonna be asked for. And then your final conclusion. Those are kind of the three main pieces. You've gotta identify everything else that they give you, but the setup, the calculations, and the formal conclusion are the key parts. Alright. It's Friday. Let's go home.
Yeah,
Alright.
let's go to work.